What's up guys, this is Massey. Welcome to another video. In this video I want to show you how to find out the equilibrium constant when we are dealing with gases. When the concept of Kc and Kp and the relationship between Kc and Kp. Equilibria involving gases also can be described in terms of pressure. We know that we have this equation for gases. PV equals to nRT. P is the pressure, V is the volume, N is number of moles, R is gas constant, and T is temperature. Then we divide both sides by V, so it's going to be P equals to N over V times RT. N over V is going to be C, which is molar concentration. As we saw in previous video, when we are talking about an equilibrium expression, for example for ammonia synthesis reaction, K will be equal to NH3 to the power of 2 over N2 times H2 to the power of 3, because the reaction is N2 plus 3H2 gives us 2NH3. And for the equilibrium expression, we write the products in the numerator and reactants in the denominator. And the exponents here are exactly the same as the coefficient we have in the balanced reaction. For example, the coefficient here for the NH3 is 2, so we make it to the power of 2. For example, for hydrogen is 3, we make it H2 to the power of 3. So it means that the molar concentration of ammonia to the power of 2 divided by molar concentration of N2 times molar concentration of hydrogen to the power of 3. So that's called K or Kc. Both of them are the same. So instead of Kc, most of the time we write a K. On the other hand, we have another term called Kp, which is the equilibrium expression or equilibrium constant for gases. And it is in terms of pressure instead of molar concentration. Based on this relationship, P equals to CRT or C equals to P divided by RT. So Kp equals to pressure of ammonia to the power of 2 divided by pressure of nitrogen times pressure of hydrogen to the power of 3. So K and Kc are used commonly for an equilibrium constant in terms of molar concentration. On the other hand, Kp represents an equilibrium constant in terms of partial pressure, as you saw it here. Let's see an example. The reaction for the formation of nitrosyl chloride, 2NO plus Cl2 gives 2NOCl, all of them in gas phase, was studied at 25 degrees Celsius. The pressure at equilibrium were found to be pressure of NOCl is 1.2 atm, pressure of NO 5 times 10 to the power of negative 2 atm, and pressure of chlorine 3 times 10 to the power of negative 1 atm. Calculate the value of Kp for this reaction at 25 degrees Celsius. So all these pressures are the equilibrium pressure. So it means that for finding Kp, we need to use this formula. So Kp will be equal to partial pressure of NOCl to the power of 2 divided by partial pressure of NO to the power of 2 times partial pressure of chlorine. So partial pressure of NOCl is 1.2 to the power of 2 divided by partial pressure of NO 5 times 10 to the power of negative 2, and partial pressure of chlorine is going to be 3 times 10 to the power of negative 1. So Kp will be 1.2 times 1.2. That's going to be 1.44. And in the denominator we have 0.05 times 0.3. It's going to be 0.015. 1.44 divided by 0.015. That's going to be 96. So 96 is going to be the equilibrium constant. Now let's see the next example. In the next example, it says calculate the value of K at 25 degrees Celsius for the previous reaction. So Kp was P of NOCl2 over P NO to the power of 2 times PCl2. On the other hand, K is going to be CNOCl to the power of 2, C of NO to the power of 2 times C of Cl2. So if I write it in terms of pressure, it's going to be P NOCl divided by RT to the power of 2 P NO over RT to the power of 2 and pressure of Cl2 divided by R2 based on the RT, based on the formula I showed you in the first page and the one that we developed here, C equals to P over R2. Then we sub all the numbers and K is going to be 4.6 times 10 to the power of 4. There is a relationship between K and Kp. K will be equal to Kp times RT to the power of delta N. R is the gas constant in terms of, and the number is 0.08206, and the temperature is in terms of Kelvin. In this case is going to be 298 because you need to convert 25 degrees Celsius to Kelvin. And what is delta N? Delta N is the summation of coefficients in products minus the summation of coefficients in reactants. So for example, in this case, delta N the products we have 2, and on the reactant side we have 2 and 1. So it's going to be 2 minus 3. So forget to put the negative in here. So that's going to be -1. So K equals to Kp times RT. So the relationship between K and Kp is K equals to Kp times RT to the power of negative delta N. And on the other hand, Kp equals to K times RT to the power of delta N. So that's the relationship between Kp and K. Let's see another example. The following equilibrium pressures at a certain temperature were observed for the reaction 2NO2 gives 2NO plus O2. The pressure of NO2 is 0.55, pressure of NO is 6.5 times 10 to the power of negative 5 atm, and pressure of oxygen is 4.5 times 10 to the power of negative 5 atm. Calculate the value of for the equilibrium constant Kp at this temperature. So Kp will be equal to pressure of NO to the power of 2 times pressure of O2 divided by pressure of NO2 to the power of 2. So the pressure of NO is 6.5 times 10 to the power of negative 5 to the power of 2. Pressure of O2 is 4.5 times 10 to the power of negative 5. And the pressure of NO2 is going to be 0.55 to the power of 2. So let's calculate it. Numerator is going to be 1.9 times 10 to the power of negative 13. And denominator is going to be 0.3025. So 1.9 times 10 to the power of negative 13 divided by 0.3025. That's going to be 5.28 times 10 to the power of negative 13. So that's the value of Kp. So that's basically how we find out the Kp. At 327 degrees Celsius, the equilibrium concentration are methanol 0.15 molar, concentration of carbon monoxide CO is 0.24 molar, and the concentration of hydrogen is 1.1 molar for the reaction. Methanol gives carbon monoxide plus 2H2. Calculate Kp at this temperature. So what we need to do here, we had earlier the relationship between concentration and pressure. C equals to P over RT, or P equals to CRT. We need to find out Kp. So Kp will be equal to CRT, the concentration of hydrogen, to the power of 2 times concentration of CO times RT to the power of 1 divided by concentration of methanol times RT. So when you simplify it, it's going to be concentration of hydrogen to the power of 2 times concentration of CO divided by concentration of methanol times RT to the power of 2. Because here that's going to be 3 minus 1 is going to be 2. So that's how we find out the Kp. So Kp, concentration of hydrogen, is 1.1 to the power of 2. Concentration of carbon monoxide is 0.24 divided by concentration of methanol, which is 0.15, times R. The value of R is 0.08206, and the temperature in terms of Kelvin is going to be 327 degrees Celsius plus 273, which is going to be 600 Kelvin. So that's going to be 0.08206 times 600 to the power of 2. So that's going to be, that's multiplication. Kp will be 4693.22. So that's going to be the value of Kp, and that's how we find out the equilibrium constant for gases. Let's see another example. Here it says at 1100 Kelvin, Kp is 0.25 for the reaction 2SO2 plus O2 gives 2SO3. What is the value of Kp at this temperature? So we already saw the relationship between K and Kp. We know the Kp, we need to find K. So K will be equal to Kp times RT to the power of negative delta N. Delta N in this case is going to be the summation of number of coefficient in the product minus reactant. So 2 minus 3. So it's going to be negative 1. So we have K equals to 0.25. That's Kp. R is 0.08206 times temperature is already in terms of Kelvin, 1100 to the power of negative delta N. Delta is L in already negative 1. So times negative is going to be positive. So positive 1. So I don't need to write the exponent, so it's 0.25 times 0.08206 times 1100. That's gonna give me 22.5665. So that's how we find out the relationship between Kp and K. Let's see another example. It says write expression for K and Kp for the following reaction. I'm going to start with K. First of all, we need to check that if it's already balanced. Nitrogen is balanced, constant C is balanced, H is 6 here, here 6, and oxygen 2 here and 2 here. Okay. So I'm going to write the products first. N2CH4O times H2O. And here, since this one in terms of solids, this phase is solid, we don't write it. We just write the gases and aqueous phase. So H2O divided by NH3 to the power of 2 times CO2. So it's going to be H2O divided by NH3 to the power of 2 times CO2. Now if we want to write Kp, Kp is going to be pressure of H2O divided by pressure of ammonia to the power of 2 times pressure of carbon dioxide. Next example. Write expressions for K and Kp for the following reaction. So here we have gas, gas, and this one is solid. So we don't write this one. We have only the products in the equilibrium expression. So K will be N2, the molar concentration of N2 times the molar concentration of bromine to the power of 3 because the coefficient is 3. If I want to write in terms of Kp, it's going to be pressure of nitrogen times pressure of Br2 to the power of 3. So that's how we write the K and Kp for this reaction. And this one, again, we need to write an expression for K and Kp. This one is solid phase, gas phase, liquid phase, and gas phase. As I said, we don't write solids and liquids. We only write for gases and aqueous phase. So K will be concentration of H2O divided by concentration of H2. And when we write in terms of Kp, it's going to be pressure of H2O divided by pressure of H2. So that's going to be the equilibrium expression for this reaction. I hope you enjoyed this video. Please leave me a comment if you have any question. Thank you for watching and have a great day.